Welcome to lecture number 9 in Multiple Antenna Communications at Linköping University. In this lecture, we will focus on the downlink communication. We will first go through the system model, then we'll talk about precoding, and finally we will go through some capacitor lower bounds, first for any precoding and then for maximum ratio precoding. And we will wrap up by comparing the expression that we can get in the uplink and in the downlink and see some of the differences and similarities. So we're considering the downlink communication now from one base station to k users. So for user I, we have a channel vector of length m because we have an m antenna base station. And this vector that we call gi to user I contains gi1 to gim. So this is a vector of length m. And the base station, since it has m antennas, it needs to send an m-dimensional signal. And we will write it as x, which is an m-dimensional vector, times rho downlink, which is a transmit power, and then we have a square root of that one. So this is the signal that is sent by the base station, and this is the channel to that user. We will now characterize the received signal of user I. So remember, the transmitted signal was x times the square root of rho downlink. We had a channel vector to this user, that was gi, and then we need to, of course, to have additive noise, wi at user I. And we have normalized things, so we have a variance that's equal to 1, it's a Gaussian noise. Then the received signal at this user is called yi. It's going to be an inner product between the channel vector and x, but it's just a transpose here, so it's actually an inner product between gi conjugate and x. And that is because we are getting each transmitted signal multiplied with the corresponding channel coefficient in gi, so there is no complex conjugation or anything like that going on. So we just get this x multiplied with gi transpose, and then we have the transmit power, and then we add the noise. So this is a received signal from one of the users, but we can write all of this in one matrix vector description like this. So we can take the received signal y1 to yk and put them in a k-dimensional vector that we call y. And then we are considering a channel matrix G, where each column is one of the channels from a user to the base station. So here we have user 1, user 2, up to user k. And this is actually the same matrix that we used in the uplink. But what we need to do is to take the transpose of it, so that we are getting a transpose on each of the columns, and we can multiply it with x, the transmitted signal. And then we have rho downlink here. And finally, we have w, which is our k-dimensional noise vector. So w1 to wk, these are the receiver noise at each of the k users. And we have parameters that are normalized here to keep it simple. So the maximum power that the transmitting base station can use is rho downlink. And we are making sure that it is not transmitting with more power than that by saying that x should have a norm which on the average is smaller or equal to 1. And this expectation is describing that when we are modulating our information signal, we are allowed to vary the power around the mean value that makes sure that it's equal to 1. And the channel of user k was contained in this kth column here, gk1 to gkm, and they are independent of each other, and we have a complex Gaussian distribution. Beta k is still the large scale fading coefficient. So this is the same channel model as we were considering before. IID Rayleigh fading for each of the users, but different large scale fading coefficients. And we have normalized noise, so W vector here is complex Gaussian. We have an identity matrix of size k as the covariance matrix. And we need to select the signal x that the base station is going to transmit, and it's containing signals that are supposed to be sent to each of the different users. So for user k, we have a message symbol qk, and just as before, it has an absolute value square, which is on the average equal to 1, and has 0 mean. And apart from that, it can be any type of codebook that is used to code information into a symbol like this. And then we are summing up the symbols that are meant for all of these k users. But we also have two other terms here, because we need to take these scalar numbers that are represented data signals, and we need to map them to our m different signals in order to determine how we are transmitting the signal to different users. And that is where we have this m-dimensional so-called precoding vectors. So AK is a precoding vector of length m that is telling us in which direction are we sending the signals to user K. And we are making sure that this precoding vector is normalized in the sense that its squared norm on the average is also equal to 1. Since AK is selected typically based on estimates of the random channel, so it's also a random variable, then we need this averaging over that randomness. And finally, we have power that we need to allocate between the different users at the base station. So we have these power control coefficients, eta k, which should be smaller or equal to 1, just as in the uplink. But in addition to this, we also need the total power from the base station to be equal to rho downlink. So that turned into that the square norm of x should have an expected value that is smaller or equal to 1. And if you compute that value here, since we have independent data symbols and each of these vectors here for the precoding have an expected value that's equal to 1, we will get a total power constraint. So in addition to that each of the eta k parameters should be smaller or equal to 1, actually the summation of them should also be smaller or equal to 1. So this is the power constraint that matters. And it tells us that we have total power budget of rho downlink. We have normalized everything, so that it's the eta k parameter that is telling us how we are dividing the power between the users. And then it should be smaller or equal to 1 here. If we take each of these eta k parameters to be equal to 1 divided by k, then we are allocating the same power to all the users, and we're using the full power budget for doing that. But this is just one option. In this video we will consider fixed values on the eta k's, but in a later video I will consider how we are optimizing them as well. So what we would like to do is to compute the capacity, or actually capacity lower bound for a system like this. So how much data can we transmit to each of the different users? And remember this capacity lower bound that we have been talking about before, where if I have a desired signal x, it is scaled by a transmit power rho, it goes through a scalar channel that we call G, we add noise W, and then we get y, which is equal to square root of rho times G times x plus W. And in this case, we are saying that we have a G, which is deterministic channel coefficient, and is known at the receiver. So there's no additional side information here. It's only that we observe Y, and we would like to guess X based on that. And then we talked about in the previous video that the capacity lower bound that we can achieve in this case is that the capacity is smaller or equal to log 2 or 1 plus a signal to interference and noise ratio, which is like taking the transmit power rho. Take the absolute value square of the channel coefficient G, and then we divide with the variance of this term W. And we have equality here when W is something that is complex Gaussian and independent of X. But in general, W might not be Gaussian distributed, it might not only contain noise but also interference, it might even contain part of the desired signal X, but we can still use this bound here as long as we have a W term which is uncorrelated with X, and that is what we're going to do. So we look back now at this received signal at user I. So yi is equal to the channel vector gi with the transpose, and then here we have the transmitted signal, and here we have the noise term. So transmitted signal when we're using precoding is a summation over all of the users. We have the total transmit power, we have the eta k parameters that is telling us how we are dividing the power between the users. We have the precoding vector of user k, and we have the data that is transmitted towards user k. And we can now rewrite this by pulling out the term that is the desired one. It's this one. So we have the power, we have the inner product between the channel and the precoding vector of the user of interest, and here we have the signal meant for user I. So this is the desired signal. The rest here is containing interference plus noise. So we have the same summation as before, except that we have removed the term that where k is equal to I. And then we have the same noise term here. And this is going to be interference and noise. And we would like to put it into this W term that we were considering in the capacity lower bound. However, the problem is that the receiver doesn't know the channel here. It doesn't know GI transmit. We didn't have any mechanism for the receiver in the downlink, the users, to know the channels. We didn't send any pilots or anything like this. And in general, you could do that, but it's not necessary in a communication system. The important thing is that we are sending pilots in one direction, namely in the uplink, so that we are able to estimate the channels there and select the precoding vectors in such a way that this inner product becomes sort of predictable to us as a receiver. The meaning of that can be different in different contexts, but when we have many antennas, we can know that the inner product between a precoding vector that is selected as a function of an estimate of the channel vector will be approximately equal to its mean value when the number of antennas is large. And that is, for example, going to happen if we are selecting A to be identical to GI conjugate, then we get the square norm of GI here, and then we know from channel hardening that should be similar to its mean value. And for any other reasonable choice of precoding vector, we will make sure that the same thing is happening. Since the mean value is obviously not random, we can assume that the user knows that value, even if it doesn't know the particular realization that we have in this coherence interval. So we would like to make sure that we get this expectation over this inner product into our received signal expression. And we will do it in a very similar way to this use and then forget technique that I talked about in the uplink. But we don't call it use and then forget because actually the receiver never knew it, so it cannot use it and then forget about it. It never knew it. But the principle is the same mathematically. So we have this received signal where we have the desired signal, and then we had interference plus noise. And we would like to have an expected value here with respect to this inner product. So let's just replace it like that. So here we have this expected value that we would like to have. So this is the same term except that I've added this expected value. But of course I cannot just add it there. I need to then subtract it again here. So if you consider these two terms, the expected values are cancelling out and we get the same term back again. And then here I have still the same interference plus noise terms. And now we could actually use our capacity bound. So in this first term here, what we have is a power scaling, which is representing the rho term in the capacity lower bound. Then we have a deterministic or fixed, a constant channel, which is representing our G. And then we have the information that we would like to convey. Qi is representing the Q in the capacity lower bound. And then the rest here is what I call a scalar value W, which is the W in the capacity lower bound. This is interference plus noise. It's not going to be Gaussian distributed because we have random data multiplied with random channels. But the important thing is that this term is going to be uncorrelated with this data here. That is namely what happens if you take the inner product between these two terms. We get a zero mean from this term and we get zero mean from this term. So we have an uncorrelated signal. So this is almost like an additive white Gaussian noise channel with the constant channel response here equal to the expected value of this inner product. And we can use our capacity lower bound. We should get this rho term, we put it here, we get the G, we take the absolute value square of it, and then we divide with the variance of this entire term. And getting the numerator is easy. We just take all these constants, we put them in here. Computing the variance of this part is taking some more effort, but we can do it. And in that case, this is the expression that we're going to get. So in the numerator, we get rho downlink times eta I. So this is the transmit power to user I. Then we get this expected value within the product that we wanted to have as our channel. We get the absolute value square. And in the denominator, what do we get? Well, we actually get the total power of all the received signal. That is this term here. And then we subtract the part that is in the numerator. So this is what we get by computing the variance of the W. And all these expectations here are computed as averaging over the small scale fading. In the numerator, we get something that is proportional to the absolute value square of this channel part that we know, which is constant. And in the denominator, we get the sum of interference from all the users, the noise term, and then the subtraction of the part from the user of interest. So this is a capacity lower bound that we can use for any choice of precoding vectors AI. And the more channel hardening we're having, the better this bound is going to be, the closer it's going to be to true capacity when actually the expected value of this term is very close to the actual realization that we get in every coherence interval. But I would like to stress that there's no approximations involved here. We are making sort of a suboptimal choice of a receiver where we are saying we won't even try to estimate the realization of the channel, where we just pretend as if it was equal to the expected value. That is the suboptimal choice that we are making, but we can do suboptimal choices and get a lower boundary capacity. There is no approximations involved. So we can use this expression to compute the capacity lower bound for any precoding that we like, but we just need to compute expectations. And that is something that you can either do by hand by computing these expectations, so you have inner product between Gaussian vectors, for example, or something that depends on Gaussian randomness. And in some cases you can compute that things by hand. But in other cases you could make a so-called Monte Carlo simulation to compute these expected values numerically. So among all of the possible precoders that we could select, what would be a good choice? Well, that is generally quite hard to answer. In the uplink we were able to derive the optimal type of receiver filter. There was something that I call MMC combining. And in that case we got a capacity lower bound that contained a signal to interference and noise ratio, which was a Rayleigh quotient of the combining vector. So it meant that it only depended on one combining vector, which is natural in the uplink. You have a base station that is receiving a signal. You try to differentiate one of the transmitted signals from all the interference and noise. And you just do that by selecting one filter for one user. But in this capacity lower bound for the downlink, we have all of the precoding vectors in the same expression. We have AI for user I, and we have AK for user K, and we have a summation of all of the users. So all of the AK vectors need to be selected jointly somehow. And the choice that we make for one user will affect all of the other users as well. So one choice of AI might be focusing the signal on one user and make its numerator as large as possible. But it might also create a lot of interference in the terms of other users. So how should we then select the precoding? Well, let's go back and think about the uplink processing that we were talking about. So the MMSC receiver was to take the receiver filter, which was also written with an A notation. So AI was selected as the channel estimate of user I, and then we had a matrix that was containing channel estimates of all the other users and noise and estimation errors. So that means that we are starting with the channel estimate of that user, and we are then rotating the vector based on where we have a lot of interference in order to sort of get rid of some of the interference and balance between getting a strong desired signal and limiting the interference. And then we consider the simplified version where we were removing these terms here and only considering the estimate of the channel. That is a maximum ratio processing, and that was motivated that okay, when we have a lot of antennas, then we will anyway be able to separate the users very well, so we can have a much simpler type of receiver. And the precoding principle that I am suggesting is that we should transmit in the direction where you heard the users most clearly. So what does that mean? Well, we are considering what was a good uplink processing. In which direction should we point our vectors to get a good trade-off between having a strong signal and little interference. So when we are transmitting back to the users, we should consider how we were processing the uplink signal from the corresponding user and use that as a guideline. So that means that the downlink precoding should be selected to be equal to the corresponding uplink processing. So we can consider a MMSC precoder where we take the same precoding vector as before, then we multiply with the factor Ci, because earlier AI could have any norm, we didn't have to care about the power. But in the downlink, AI was supposed to have a squared norm, which on the average is equal to 1. So we take this scaling factor, we are computing the expected value of the squared norm of the rest of it here. We take the square root of that and we divide with it, and then we multiply it in front here, making sure that AI have on the average a norm which is equal to 1. And a simplified choice is maximum ratio, where AI is equal to just the estimate of the channel, and then we need to normalize this one as well, so that AI have a square norm which on the average is equal to 1. And the same principle, we put Ci being equal to 1 divided by the square root of the expected value of the square norm of Gi hat. So in that way, AI points in the same direction as the channel estimate, but we are making sure that on the average is a unit norm vector. So we can take any of these precoding vectors and put them into the capacitor lower bound that we had before, and then we just need to compute the expectations in order to get the capacitor lower bound. And for the MMSE case, it turns out that we cannot actually compute the expectations exactly. We need to run simulations to approximate them. But when it comes to maximum ratio, we can compute the expressions. And then we need to remember, how did we select things based on the channel estimates? Well, the MMSE estimate of user K to antenna M, GKM, that channel have an estimate that we were computing by taking the received pilot matrix after the dispersion operation multiplied with the scalar, and then we are getting something that is complex Gaussian distributed and have a variance gamma K which had this expression. And remember, it contains tau p, which was the length of the pilot, rho uplink, which was the transmit power, and then we have beta k and beta k square, and we have 1, which is the noise variance. And the estimation errors were containing beta k minus gamma k, so this gamma k is an important parameter. And based on this, we can compute all the expectations, and the result is the following. The downlink capacitor lower bound with maximum ratio processing have this form. The capacity of user I is smaller or equal to log 2 or 1 plus a ratio, which contains a numerator, which is the desired signal, and a denominator with interference plus noise. And there are no expectations left here because we have computed them with respect to the small scale fading, so they are not visible on this bound, which is sort of its good feature. Then we can understand how the system works. So if we look at the numerator, what we have here is that we have a coherent beamforming gain. So we having a term that is growing with number of antennas m, which is sort of what we were getting in the MISO cases earlier. But now we have multiple users, but we can still achieve that beamforming gain. And then we have the transmit power that is allocated for the user, rho downlink times eta I. And then we have the estimation quality gamma I. So it's not beta I that's showing up here, but the estimation quality, because our beamforming is not better than the estimate is. Then in the denominator, we have a summation over the interference related to all of the different users. So we have the power that was allocated to user K, and then we have beta I, which is the channel gain to user I. So not user K, that is meant to get the signal, but the receiving user I that we are considering. And then we have a 1 here representing the noise variance. And once again, I will call this non-coherent interference for the reason that it doesn't grow with number of antennas. Even if we are beamforming more and more towards the different users, the interference that is caused between the users is not growing with number of antennas, which is showing us that it's beneficial to have more and more antennas because the desired signal gets a beamforming gain, but not the undesired interference terms. This capacitor lower bound is actually quite similar to what we got in the uplink when using maximum ratio. So let's put them side by side, here for the uplink and here for the downlink. And they have a quite similar structure. They have log 2 or 1 plus a signal to interference and noise ratio, which essentially all capacitor lower bounds are having. But then in the numerator, we also have the same structure. We have a beamforming gain, and then we have a channel estimate, eta I, which is the same in both cases, and then we just are denoting the transmit power differently. So we have rho uplink eta I in the uplink and rho downlink eta I in the downlink. But apart from that, it's the same. We're just switching uplink to downlink. We have a similar structure also in the denominator. So we have a noise variance 1, and we have a summation over the interference for all of the different users. And we have rho downlink eta k as the transmit power for user k in the downlink, and we have rho uplink eta k for the transmit power of the user in the uplink. But one key difference here is that in the uplink, in each of the terms here we have a different beta k. So the interference from user k goes through the channel from that user to the base station. So therefore the large scale fading coefficient of user k is showing up here. However, in the downlink, all of the interference is transmitted from the same point, from the base station. And even if the signals are meant for another user, it's going to go through the channel from the base station to the user's eye that we are considering. So that's why we have the same term beta I in all of these interference terms here. So this is the main difference to remember. Uplink interference comes from different users through different channels to the base stations. And in the downlink, all the interference is coming through the same channel from the base station. They are assigned to different precoding vectors, but the signal is still reaching the user in the same way, and that's why the same beta I is showing up there. I will now wrap up this lecture by considering 4 simulation examples where we're considering both the uplink and the downlink. So let's consider first the uplink rate with a varying signal-to-noise ratio. So I'm assuming that we have 10 users. All of them have, for simplicity, the same value beta equal to 1 as their large-scale fading coefficients. Tau p is equal to k, so that's the minimum length of the pilots that we can have. 1 pilot per user requires a pilot length equal to k. And then we'll let all of the users transmit with full power, so eta k is equal to 1 for all of the users. Then the graph here is showing the rate or the value of the lower bound of the capacity in bits per second per hertz. And we are considering maximum ratio processing, and we are changing the number of antennas here. And we have 4 different curves representing different signal-to-noise ratios. Because I've normalized beta to be 1, rho uplink is actual the signal-to-noise ratio. The lowest curve is when rho uplink is minus 10 dB. Then we have minus 5 dB, 0 dB, and 5 dB. So as we are increasing the SNR, we get a larger rate for the user. And we see that we are moving 5 dB every time, but the gains are larger in the beginning than later on. And the reason for that is that we have 2 effects from the SNR. One is the estimation quality, which becomes better with the SNR, and the other one is that we have, of course, a better SNR during our transmission as well. And that is what we are seeing here, that we have a rather bad channel estimation quality in the beginning when we are starting with minus 10 dB. But then as we are increasing the SNR, we get a good channel estimates, and then we have a smaller gain of increasing the SNR further. And remember, I've computed all these curves using that closed form expressions that we have developed, and there in the numerator it was the gamma k that was showing up the estimation quality. When gamma k is similar to beta k, then it doesn't change very much when we are increasing the SNR. So we only get one benefit of increasing the SNR, namely that the transmit power during the data transmission is better. But when we are starting at a low SNR, then both gamma k is approaching beta k much more, and we get a gain during the data transmission as well. And we can also see here that for all of the different curves, as we are increasing the number of antennas, the curves are going upwards. And in the beginning, it's almost linear because we are starting at a relatively low performance, and then we are not in the logarithmic range yet of the log 2 or 1 plus the SINR expression. But then when we are reaching a larger number of antennas, we see this logarithmic behavior, and we see smaller and smaller gains of adding further antennas to the system. So it's always better to have more antennas, but in particular when we have a small number of antennas and increase it, then we are seeing large gains. So up to 100 or 200 antennas, that is when we can expect the largest gains in the system. So this is an uplink simulation, but the result is also applicable in the downlink. If we assume that all of the betas are the same, well then that difference in the interference term goes away. The only difference that remains is how do we select our power allocation and what is the transmit power. So if we are assuming that the downlink power is k times the uplink power, so the sum of the power from all of the users equal to the total power that the base station have available, and then we divide that power equal between the users by selecting eta k to be 1 divided by k, well then we will get the same power per user both in the uplink and the downlink. And that is quite realistic because a user device is powered by a battery and it's close to the user, so it has a limited power budget that it's allowed to transmit with. While the base station is elevated, so it's far from the user, so it's allowed to transmit with more power, and it also is connected to the grid, so it can transmit with more power without it being a problem. So it's typical that you have a 10 or 100 times more power at the base station than at the users. So I would say that this example is perfectly alright both in the uplink and the downlink when we are selecting the parameters like this. Next we consider the same setup we set the row uplink to be minus 10 dB, so it's the lowest of the curves, and we are instead comparing maximum ratio processing, which we had in the previous graphs, with the MMSC processing that I've been talking about as well. And we see the same type of trends here. So as we are increasing the number of antennas, the performance goes up. We see the same trends, namely that as we increase the number of antennas, the rate is going up, both with maximum ratio and with MMSC processing. But there is also a substantial gap between them. So we can get a 60 to 100% higher rate using MMSC processing than maximum ratio. And as we increase the number of antennas, this gap will actually still remain, at least to some extent. So that means that it's always better to use MMSC processing than maximum ratio. In the uplink, MMSC was the optimal choice and maximum ratio was a simplified choice, while in the downlink, both of these ones were sort of suboptimal in the sense that we use this principle that, okay, what is good in the uplink should also be good in the downlink, even if it's not good in an optimal sense. But this means that maximum ratio is a good choice to have a simple implementation and to get this closed form expression where we can understand how the system works, while MMSC processing is a better choice that you should ideally use in practice in order to get more performance out of your system. We will now move on and consider the uplink in a case where we are changing the number of users. We still have beta equal to 1, tau p equal to k, and every user is transmitting with full power. And we consider it maximum ratio processing. And here we are showing the rate per user as we are varying the number of users from 1 up to 20. And we consider two different cases. One of them is where the number of antennas is fixed to be 100, and the other case is when we have 10 times more antennas than we have users. So these are two different curves here. When we increase the number of antennas with the number of users, we can see that as we increase the number of users, the performance is actually going up. So we are both adding users and antennas, and the users are getting better and better performance. What is the reason for this? Well, there are two factors that are improving the situation for us. One of them is that as we increase the number of users, we are increasing the number of pilots, and therefore the estimation quality becomes better. So gamma k is growing with the number of users. The second effect is that as we increase the number of antennas and users at the same time, both the signal term and the interference term is growing at the same pace, leaving the noise term behind. So that means that the noise variance plays a smaller and smaller role, and that is also improving the rate for every user. If we are instead considering the case when the number of antennas is fixed and we are increasing the number of users, then what we see here in the beginning is that the rate still goes up as we add more users. The reason for this is that we are still considering a signal to noise ratio being minus 10 dB, which means that as we increase the number of users, we are also increasing the length of the pilots, and therefore we get better channel estimates, and that is a dominant factor here in the beginning. We add more users, we get better channel estimates. We could of course have kept the length of the pilots fixed and have a larger tau p number of users, but that's not what we're considering here. Then after a while, the benefit of getting a larger gamma k is outweighed by the fact that we get more interference between the users. Because now the signal term in the capacity expression is constant because we have a constant number of antennas, but the interference term is growing in proportion to the number of users, and that is bringing down the performance per user. And we can see that the two curves are crossing at the occasion when we have 10 users and 100 antennas in both of these different curves. So then we are considering exactly the same setup. And if we were to consider an MMSC processing instead of MR processing, we will see the same type of behaviors here, but higher rates for all the different methods. Finally, if we consider the same setup again, but now instead of looking at the performance per user, we are considering the sum of the rates of all of the different users. Then we still have the same setup. We still have the two curves where we either have 100 antennas and a varying number of users, or we have a varying number of users and always 10 times more antennas than users. Then we can see that the sum rate is going up with the number of users in all of its different setups. So even in the cases in the previous simulation figure where the rate per user went down, So that was happening when we have 100 antennas and a varying number of users. Then we are still seeing that the sum of the rates for all of the users are going up. So it actually is still beneficial for the system as a whole to add more users into the system because we are sending more data in the cell. And when we have deployed a real system with a fixed number of antennas, this is what's going to happen as we are varying the number of users. If you increase the number of users that we are serving, then we will get lower performance per user, but a higher sum rate. And if we are instead considering how we should build a network, well then we can consider this setup where we have 10 times more antennas than users. And then we can see, okay, I would like to build a system that is able to handle 15 users, and then from that we can figure out what kind of sum we will get. And we see that as long as we are following this rule that we have a proportional number of antennas as users, the sum rate is growing proportionally to the number of antennas and users. And we can observe a similar behavior if we would consider an MMSE processing. This figure was about MR processing in the uplink, but the qualitative behaviors would be the same. So what are then the benefits of using MR processing? Because we saw that MMSE processing is performing better. We get 60 to 100% better performance per user in the simulation set that we considered. One key benefit is a lower computational complexity that MR have compared to, for example, MMSE processing. So we just take the channel estimate and we use it as a receiver filter and as precoding vector. And that stands in contrast to MMSE, where we also need to invert a matrix in order to compute our precoding and receiver filter. And of course there is a big gap in performance, at least in theory. But in practice, it is much easier to implement max ratio. So real products containing massive MIMO will first use MR, and then after a while we might also be able to use MMSE processing as well. But when all types of engineering issues around synchronization of this and that, all of the small details that is affecting a real implementation will hurt MMSE processing much more than MR, because they are relying much more on the ability of cancelling interference, which is requiring a larger accuracy in all of the computations that we are doing. Another benefit of MR is that we can get closed form bounds on the ergodic capacity. So the typical shape of an ergodic capacity bound or ergodic capacity itself is that we have an expected value of the logarithm of 1 plus an SINR expression, which is a random number. So it depends on the realization of the channel in a particular coherence interval, and then we compute an expectation with respect to that. And what we have been doing when we are dealing with maximum ratio is to treat the channel as being equal to its mean value. And then we get capacity bounds that looks much more like an additive white Gaussian noise channel, where we have log2 of 1 plus an SINR expression which is now constant. It doesn't depend on the randomness of the channel. However, in this expression there are still expectations with respect to that randomness, but when we are using MR we can compute all of those expectations in closed form, and we get a very simple expression for the entire ergodic capacity, and we can understand the different parts, how the number of antennas is affecting the capacity, how the large-scale fading coefficients and the estimation quality comes into the picture, the interference, everything is there in a neat form. So this is a very useful way of understanding the ergodic capacity behaviors when we are dealing with massive MIMO. So in summary, what we have been talking about in this lecture is the downlink communication. We developed a rate expression that we can apply with arbitrary precoding. We just need to compute the different expectations in some way. And we're computing them in closed form with MR precoding. An insight that we were obtaining was that the uplink and downlink rate expressions are very similar. They're containing almost the same terms, but we have transmit powers in the uplink that have a different notation than transmit power in the downlink. And also the interference comes from different places in the uplink and the downlink. In the uplink, every user is sending interfering signals, so they are going through their channels to the base station, while in the downlink, all of the interfering signals are sent from the base station. So it's only the user's own channel that comes into the SINR in the capacity expression. We observe that MMC combining is substantially better than MR, but we are still seeing the same type of trends in both of the cases. And MR have the benefit of being much easier to understand the capacitor expression. For example, in all of the simulation example I was showing, computing the expressions with MR takes no time at all. While with MMC combining, we need to run large Monte Carlo simulation where we are computing the expectations randomly by considering a large number of random realization and average over them. And finally, we observe that when we are increasing the number of users in the system, so we get more interference, well then we should increase the number of antennas as well to get the beamforming gain that counteract that effect, and then we can both get the sum rate to be larger and keep the same performance or better performance per user than before we increase the number of users. So that's the end of lecture number 9 in multiple antenna communications.